In this tutorial, I'd be mostly taking a quick recap of things that were covered in the lectures. So you should still consider the lecture videos as your primary source to get the core ideas. This would be like a recap, solving a few questions, some from the lectures itself if you have any doubts in those, some just extra so that you can solve the assignment questions and maybe even be able to do well in your exams at the end of the course. Okay, so I'll start with a quick recap. If you have any doubts at any point, you can just raise your hand and ask questions. Okay, so this has to be an interactive session, that will be good for you. Alright, so the things that were covered in this week were very introductory things. So sir started with the definition of what a game is, then a concept called Nash equilibria concept, then the idea of dominance, or when a strategy is stronger than all the others. Then there were a couple of definitions, strictly dominated and weakly dominated. And then in the process of solving a few examples, after that he gave you some theorems and corollaries that sum up things that can be considered when we are dealing with these types of strategies. Okay, so as a quick idea, you can think of games, actual games also, under this kind of a theory. The idea here is to try and find out from the perspective of an observer. So you're not taking the viewpoint of either of the players, you're not focusing on what should a player do so they win. That's not the objective. The objective is you're an observer who's saying what kind of steps they would take. So you can take, for example, a game of rock paper scissors. So let's say it's just two players, so I'm representing those players by P1 and P2. These players have some actions that they can take. They can either go for rock, paper or scissors. They can give gestures for that. But while they're deciding what to do, they are trying to make a guess or have some idea as to what the other might do, and hence choose their own decision also, their own action also. Because they know the outcome of the game in a normal setting is whether they win or they lose or there is a tie. These are the three possible outcomes. So either it's a tie, so let's say here tie is represented by 0, or there is a win situation which gives you a utility of 1 or a payoff as a value 1, or a loss which gives you -1. Right, so you can just have a look at this matrix. This matrix is basically the utility of player 1. So this is for player 1, the second is for player 2. This is the tuple. Okay, so we can take just one row as an example and try and understand like what all is happening here. So for example, let's consider this first row where player 1 is playing rock. So player 2, if he also plays rock, they would both end up in a tie situation, nothing happens there. On the other hand, if player 2 plays paper, he's the one who wins. Since someone won, someone has to lose. That's why the other player gets -1 as the utility. On the other hand, if player 2 played scissors, then he'd be the one to lose against rock and would get a -1 as utility, and the other one would get 1. So this very simple scenario captures some of the core ideas that you have already seen in the first week's lectures. Any doubts so far?
Ma'am, there is, I can ask you the same question. Like, this rock, paper, scissors can be considered as a zero-sum game, right?
Yes.
Because the sum of utilities is equal to 0 in all the cases, so it can be considered as zero-sum game.
Yes.
That's all.
Yes.
Thanks.
So what is the importance of the relative values of the payoffs? Like say, quite possible that I would like to assign the values for tie as say 15 and then win for 20. So so their relative values matter, or I mean their absolute value also matters? And moreover, in the design of a game, who is going to decide these payoff values?
Okay, so if we are taking the perspective of game theory, as an observer, as players also, the matrix is given to you. All you're doing is just looking at which one is greater than the other or smaller than the other. So it's relative that matters. The exact numbers here doesn't matter. If you were looking at it from the perspective of designing the game, then what kind of outcomes do you want at the end of the game, at the end of the whole process is over? Then the values might have more value, like they will have more significance.
So, like, say, if I want to model a conflict in between the two nations as a game,
Hmm.
then how to decide the payoff values? Do I need to? I mean, which parameters, which all parameters need to be taken into consideration while determining the payoff value so that the game reflects the real situation?
So see, it depends how complex you're going, how complex is the design of your game. If you're going for a game like the one that we have here that can be represented in a simple matrix form like this, or what is typically called as simultaneous games, then it's just numbers. You can choose whatever number depending on what kind of win or loss that you want.
Like, so from this example, it seems that as if game theory is relevant only for the limited number of the players. So what if I have something or model a conflict in between hundreds of the players on one side, hundreds of the players on the other side? Then how to model such a conflict or such a situation?
It can be done, it's just that it may, as the number of players increase, the difficulty in solving them increases.
Also, are there limitations of the game theory as well? That okay, it works fine, or can we model best only if we have the limited number of the players,
Yeah, so
or it works in general?
see, it's a model to explain how people would make decisions when uh, they're given what would be the payoff at the end of it. But in these kind of scenarios, like the one that I'm showing right now, where it's non-cooperative, that the two agents are not trying to work together, they're doing whatever they want in a selfish manner. In that case, you can always model it, but the difficulty of actually solving for a solution, for example a Nash equilibrium, may be difficult given the number of players involved, given the complexity of the strategies involved and so on.
Oh, I see.
Yeah.
And the game designer is going to decide the strategies. Is it like, or is it like this, or there is something else as well?
So as
Who
soon
is going to decide the strategies?
strategies will, in the upcoming weeks you'll get to a more precise definition of strategies, but for the time being strategies just refers to the actions that they can take. So
I
it's
see.
it's a part of the game design itself, like what kind of options do you want to give your players, and on the basis of that they'll choose and then go on further.
Oh, yes, I understand. Thanks.
Yeah. Someone else was also asking a question. Is it resolved, or uh, was it Dinesh? Okay. Okay, so I'm going to continue now. All right. So, right. So one of the words that was mentioned here was this zero sum game. Zero sum game basically means if suppose we have two players, then the utility of player 1 and the utility of player 2 for any pair. So let's say we're talking about they both taking action RR. If this adds up to 0, that's what is called as a zero sum game, and this should happen for actually all strategies or all actions. I have just written it for one. This is just one type of game. This has a nice properties. We'll eventually come to those. Okay. All right. So at this point we have seen a few examples in the lecture, so I'll just take one of the examples from there and go by the definition of what a game is. So a game is something that consists of the following things. First is the number of players. Then it's the set of strategies and the utilities. All of these three things together form what is called as a game. So we can take this as an example and write down all of these things to be sure that we actually understand this, and then go through the whole thing carefully. So this is fairly easy. Any one of you can tell me what is this n here?
N is 2.
Yeah, the number is 2, but this refers to A and B, the players A and B. If I were to write the cardinality or the number of players, then that's 2. Okay.
Yes.
And now next thing is strategies. So now see, strategy is for each player. I belongs to this. So this is for
Silent and testify might be two possible strategies, right?
yes.
There was a hardware against
Yes. So this consists of silent or testify. And this is for both of them. It's the same strategies. If we go back to the previous example of rock, paper, scissors, they also have 3 actions, and the actions are available. The actions available to both of them are same. That
What if the strategies are unsymmetric? Like say here the strategies are symmetric.
they can be.
What if the player 1 has got only 2 strategies and the player 2 is having say 20 strategies? So
It's fine.
okay.
See, that's why to consider such a scenario, the strategy set Si depends on which I you're talking about. It's in this example we don't have to worry about it. It's the same for both of them, but typically you'd write them separately. And then you could also be asked, okay, what is the number of strategies for a given scenario? Right now it's the simplest version, so we are talking about just the actions or what decisions they have available to them. So this is point 1, point 2. Now the third thing, the utilities. So if you recall, the utilities are defined as a function from the strategy space, the strategy profile to be more specific, so it considers all the agents or all the players, and at the end of it, it gives us a real number. So here this UI considers the strategy of player A and strategy of player B, and it gives us a number out of it. And this is shown in the form of the matrix here. Okay, so in a very simple form, in just this much, we have managed to capture most of the things required to describe these types of games. Now, the typical assumptions in game theory settings, or the kind of games that we'll be talking about mostly, are that first assumption is that the players are not communicating with each other. By the way, I'm saying it specifically for non-cooperative agents, non-cooperative games. Just 1 minute. Second assumption or second idea here is that they both have access to this payoff matrix. They can see this. They can see the reward, their own reward, and the reward of the other one in all the different scenarios. So they have access to this matrix, and they know that the other also knows this. So in the language that was used, this matrix is common knowledge. So for the timing, I'll just write that. So utility Yes, someone had a question. Yes, ask.
Explain, ma'am. Explain specific answer questions. Week one questions.
Have you already gotten the answers of them?
I tried, ma'am, but I don't know answer. Correct, exact answer.
No. Have the
Answer
answers
is
been released?
release, but I want explanation about the questions.
I am not supposed to solve questions from this
Just
year. I
explain.
can explain the questions. I can go through the rough ideas, but
That's one I'm asking.
okay. Uh, if you have a specific doubt, you can just ask that.
Okay, ma'am. Okay, ma'am. Once I will verify and I'll ask.
Okay, yeah, that will be better. Okay, and another thing over here is that the viewpoint that we are taking, or our idea of doing all of this in game theory, is not to try and make one player win or to say what strategies will be actually played by any of the players. All we are saying is, as observers, what can we say about the rules of how the game must be played? Okay, so we are not predicting how it will be played. We are just asking how it should be played. What are the rules, and if they go by the rules, what would be the end result? If they don't go by the rules, then we need to say what happened and hence what can happen, what can be the predicted outcome. But for now, we're just going through the basics of it, the rules of it.
Can we guarantee the winning of a particular player? If both the players plays optimally,
Mm-hmm.
then can we assure the guarantee that a particular player is going to win?
See, it depends if there is even a meaning of win in each game. There might be situations where there is no winning. Like, for example, here in Prisoner's Dilemma, neither of the players actually care about whether the other one stays in jail longer or not. They care about whether they manage to get out as fast as they can.
Okay. So which types of the problems are being modeled by using game theory? I mean, what
So,
game theory has to offer to a modeler?
right, so it can be used in a few different settings. So it can be used in economics type settings or politics type settings where you can try and model conflict or how negotiations are supposed to be done. Or people have also tried doing it for settings where you know there's supposed to be a war about to happen. Where should the troops go? I think there is a name for that particular kind of a game also. So, like, should they divide their troops, send a fraction here, send the other fractions to the other location, knowing or making a guess about what the other side might be up to? So, these kind of things can be modeled into games, into game theory settings, and we can ask if they were to behave in a certain way. So, based on some assumptions, if they were to do something, what can we expect as the outcome of the whole thing?
I see. But just now you said that this entire matrix is known to all the players.
Yes.
So I mean, in this setting, the entire information is revealed to everybody whosoever is participating. But then it rarely happens in the scenario which you indicated, like in the political situation or in the warlike situation. The
Okay.
information is all incomplete.
The information is incomplete. The information is more like you will have a rough idea what will happen if both of you take a certain action. So, for example, if you say, if I send 70% of my troop to say north, and the other side has also sent 70% of their troop to north, then what is the chance which side wins, or what is the chance how many people, how many soldiers get killed in the process? So you can have an estimate of that. So that rough estimate is enough to be able to make the decisions in the game.
More like a game of chess, basically. When you decide after like 7 moves, these are the possible combinations, and then this is it.
For now, we're restricting ourselves to the case where both the agents take their actions at the same time. So it's simultaneous games. What the other person mentioned, those game of chess, for example, it's a game where players take action one after the other. Those are dynamic games.
Oh, I see. These games are the static ones?
Yeah, for now we're dealing with static ones.
All right. Thanks.
About writing the answer.
So, ma'am, just one question. Like the prisoner's dilemma, the like the utility functions gives like positive values like, for every strategy, but it looks like a negative sum game basically. Prisoner's dilemma. So, like it should we consider it as a negative sum game or a positive sum game? Because like these returns are negative because they have to spend more time in prison. So it looks
So-
like a negative sum game.
So see, you can think of it as a minimization problem. You're minimizing. Each player, each prisoner is just minimizing the number of years they have to stay in prison depending on what action they take. So it's the exact opposite idea. So either you're maximizing or you're minimizing.
Thanks for that knowledge. Minimization problem.
Yeah. So based on the way the problem is described, you'll be able to make a guess which one it is. Otherwise, typically it will just be mentioned whether it's maximization or minimization.
Thanks.
Yeah. Okay, so this is one kind of game, and this is the basic stuff about the game. Now, to be able to talk about any kind of an outcome in these types of games, or okay, let's before we even talk about outcomes in these types of games, let's talk about a simpler situation. Here, all of the problem is the players know that there are two players. They also know what are the actions available. They also know what would happen depending on what action they take. But what utility they themselves will get depend on the action taken by the other one. For example, let's focus on only this particular case. So I'm talking about player A choosing to stay silent. Now, whether he'll get to be in jail for 1 year or 3 years, it's no longer in his hands. It depends on what was done by the other player. So, even though he himself can try and minimize his number of years, he can't confirm what the other one does, and hence it may not be so simple to make a decision. In this problem, it's actually easy to see what should be done, but in general, the difficulty in these types of games is because your utility is dependent on the action taken by the other one, and you don't know what action they actually took in the game. You know the options available, but you don't know what they actually took. So you're minimizing something that you don't have complete information about. So you're minimizing based on whatever you know to the best of your knowledge. That's roughly what happens here, and that's the kind of problems it can model. Wherever you're taking decisions which are actually affected by other people's decisions also, but you can only only take the next step based on whatever you know. Okay, so let's move forward. Now, one of the things that was introduced was this definition. This is the definition of equilibria concept, Nash equilibria to be more specific. Here, what is being said is a strategy profile. A profile is basically if we talk about the strategies or actions taken by all of the agents in the game. So, for all n of them is said to be Nash equilibria if there is a certain behavior expected in utility. Now, notice we're talking about this type of an inequality here, meaning we're restricting ourselves to game where agents are actually interested in minimizing. Okay, if it was the opposite scenario where the agents were interested in maximizing, you would be basically saying that the utility you would have gotten from the Nash equilibria would always be more than the utility you would get if, let's say, the other agents stuck to the same profile, only you changed your action. Then it's the same, it's this Nash equilibria that will give you better performance. That better may be in terms of minimizing if that's the focus.
What is capital N here?
N refers to the number of agents. We had this, right?
Oh.
So this N.
So then we would be having that n-dimensional tensor kind of a thing to know what. Because in that matrix form, we were getting the value corresponding to say 2 stars.
So it's again a value. So see, we are, so what, look what we have written here, it's UI. So UI would be either of this agent or of this agent.
Yes. But then this time this is n-dimensional, is it?
Yes, we can take N to be 2 and take an example and understand it first. People typically work with 2 to 3 agents as toy problems. At least as far as introduction of a course is concerned, you can work with more agents in principle, but the definitions should be general enough. So that's the case here.
Okay, yeah, fine. But then usually what is the size of, the usual value of capital N in the games?
It
To
depends
what
on,
extent? What is the largest value? Large value, often used in game theory.
it depends on the kind of problem people are talking about. People generally, so people who do theoretical work generally talk about N being something general. They start out by N equal to 2, come up with their rules and see if those rules generalize to any general value of N. The ones who do practicals, it depends on the exact problem that they're trying to solve. That gives them limitation on computability, solvability, like getting an answer out, getting an optimization value out. So I can't give you those numbers as of this form.
And in this notation, so x minus I, does this mean that everybody is doing the same stuff as earlier, except the ith agent? Is this or something else?
I'm coming to it. I'm coming to explaining this more carefully.
Okay.
I'll take this example and explain it. Okay. So now let's since this is a notation you're looking at for the first time, let's go through it very carefully. So now let's take this prisoner's dilemma as our example. Remember, here the objective is minimizing. So the inequality can be used in the exact form. We don't have to worry about it. Okay. So now let's write it in the following form. So we know that there are 2 action choices or 2 strategies for each of them. That means if we were to write the whole profile, how many total profiles are possible? Profile means strategy by 1 and strategy by 2.
4.
Basically 4.
Exactly. There are 4 possibilities. So let's just look at all 4 of them and see what happens. Right. So let's write them carefully. So let's say the first one is, I'm talking about agent 1. Okay, it's not agent 1, it's agent A and B. Okay, so A is this, B is this. You know what, I'm gonna switch this just to not get confused. This is A's utility, this is B's utility. Okay, so UA of, say, being silent is 1, and it just happens to be equal, it doesn't have to be. For the same profile, the utility of the other guy is also 1. So what I'm doing right now is just writing out this matrix in this form that we want. If you recall from the lectures, the claim was, what was the claim? Which was the Nash equilibria in this?
Was the Nash equilibrium.
Okay, so you're claiming 2, 2 is the Nash equilibria. Okay, let's verify. That's the main task. We want to, let's say we are told what is the Nash equilibria and we're trying to verify. So verification means we just need to check if this property holds or not. So if 2 is told to be the Nash equilibrium, which means we are talking about the strategy profile T comma T. Okay, so let's get to that. So we can write out all of them. So it's ST. Sorry. Okay, so this is the complete scenario. You can just work with the matrix itself, you don't have to write it out. The writing out is so that you get comfortable understanding this notation. So now let's focus on one agent at a time. So let's verify if the profile is correct from the perspective of agent A or prisoner A. So my focus is going to be on UA. So these are the ones that I'm going to focus on for the time being. So I am interested in checking UA something here. The suggested profile for the other is testify. So let's keep that as testify. What happens here? And compare it with the one they have given. So there are only two options available for this one. So either it's S or T. T is going to be equal, so I can just focus on S. What is UA of ST? This is 3, and this one is TT is 2.
UA of TT is 2.
Right, which means this is smaller than UA of ST. Meaning, once the player has reached this, he's decided to testify, he's not going to want to deviate from that. It's actually the right decision for him. Okay, assuming the other one has chosen to stick with that same profile. Okay.
But then what about the option silent?
Coming to that. We have not managed to verify it completely. For now, we have only said from agent A's perspective, this is the correct profile. From agent A's perspective, testifying is the right thing to do. Okay, so we have verified half of it. So we need to still verify the other half, which is, now let's look at UB. When UB is the one taking the action, he can keep his, so his action is what he can vary. He can go to S, but for the time being I am writing it as the first person's action and the second person's action. So this is still T, this is the second one's action. So this is the one that can be S.
It's not clear actually. Probably I missed something or something is not clear. So what are we trying to achieve through by showing this equilibrium kind of the thing, that howsoever or whichever strategy or whichever modification I make, I'm not going to end up with something better than this.
So it means, in words it means, if I was to change my decision unilaterally, meaning I'm the only one changing it, I'll not benefit from doing that. So it's better not to.
Oh, I see. So like in the, I mean, why this 2 comma 2 is an equilibrium situation and there is one.
I'll come to that. I haven't given you a way to verify if it is a, I haven't given you a way to find the equilibrium. Right now I'm saying, let's say we know, we are told that this is one of them. We are just verifying, is it correct or not? And verification means we are just verifying if this equality holds for whatever profile we have been given. Okay, and we see that it holds for prisoner A. Now we are just looking at prisoner B. For prisoner B, you can see what is happening here is UB of TT is 2. ub of ts, what is that? That is 3. Again, the same inequality holds. Meaning, this is the Nash equilibrium, because for our game, all of this holds. See, we were supposed to check it for all I and all strategies xi. For us, the thing xi should at least be different from xi star, only then it makes sense, otherwise it's equal, there's nothing there to check. So there's only one option to check, and there are only 2 options to check, and we did all of that, meaning we have confirmed that this is a Nash equilibrium.
So, like, say if the first player choose to remain silent, then I shall focus only on the first row. And now, what are the options available for the second player? So, the second player will also get benefit if he also remains silent, if the first row is fixed, right? So, if the first player choose to remain silent, then it is, I mean, then the player B would also like to remain silent because of the larger payoff. Now, if the player 1 choose to remain testify, I mean choose to go for testify, then in the second row, the player B will get higher payoff if the player B remains what? Player B remains silent. And so, I mean, in this thing, so I could not understand that why this 2,2 is an equilibrium kind of thing, that this is the most valuable thing for both the players and they should not deviate from this 2,2 thing and both should testify, and the other equilibrium
Okay.
does not exist. So why is this happening?
So
If you can please go beyond this equation, because this equation seems to be pretty complicated because of the n number of things.
So, okay, so this was going in the form of equations. Now let's look at it from the matrix point of view directly. So now just remember this part. These ones are for player 1, the others are for player 2. So when we are comparing player 1's utility with player 1's utility, not with player 2's utility. So the comparison will be between these two or these two, because you can't change the action taken by the other one. So you will be comparing 1 and 0 or 3 and 2. In this scenario, if you are trying to minimize, you would say, okay, wait, if he goes silent, if player A chooses to be silent, he gets more utility than if he testifies, no matter what the other guy does.
So if the player 1 remains silent, we get the utility 1. And we are looking for the lesser value, right?
We are minimizing.
Minimizing, right? So player 1 would like to remain silent. That's fine. If the player 1 remains silent, then it is also in the benefit of the player B to remain. Then this is, I mean, then the player B should testify, because then the payoff would be 0
for player B.
For player B.
Yeah.
Right.
Yeah.
And similarly, we can make this argument for the testify. But then, where is the equilibrium here? What kind of the equilibrium is here? I mean, what are we trying to achieve? To equilibrium, or by writing, by confirming this.
Let me go through it again. So one way that I like to do this to find where is the equilibrium in a particular problem is to compare in the following way. You can choose to do it either ways. You can either go through the equations like we did here, or you can just look at the matrix and do it. So I prefer doing it this way from the matrix now. So I am focusing on player A right now. So player A, if player B has chosen silent, has 2 options, either to stay silent himself or to testify, which means he get a utility of 1 or 0. For him, 0 is better than 1. So between these two, he would want to prefer this. So now I am just highlighting the one he would prefer, okay, which is this one. let's look at the other scenario. If player B had chosen testify, what would have player A decided to do? He can either stay silent and have 3 years, or he can testify and have 2 years. Between these two, 2 is always better. That's less than what he would have gotten in staying silent, meaning this is the better choice. Now let's repeat this from the perspective of B. So B would also do the same thing. B would say first assume player A is silent and then compare 1 and 0 and would be like, okay, it's better to testify. And then if he assumes A went for testifying, he would compare 3 and 2 and he would say, okay, 2 is better. So the scenario where both of them agree that this is better than what they could have done given the other player had another action tells them that this is a stable point. Or you can think of it like, if this is where they landed, they would not benefit from moving if they were the only ones moving. And remember, in these games they can't communicate, they can't tell the other one that, oh, you know what, let's try and collude and let's both do this. They don't have that option of talking to each other. So they are going to choose the action that is the best one that they can choose.
Yeah, I understood this thing. Thanks, but then I am a little doubtful that these values have been so very cleverly selected, so that
Yeah.
eventually to led to the, I mean, this thing, the equilibrium thing. This could have been a different scenario if we opt for the different payoff values. Is this?
Of course.
Okay.
If payoff values are different, then it would be a very different scenario. Okay.
Ma'am, there's a question in the assignment that once you find a unique Nash equilibrium, give us the 10x plus y. So
Okay.
here x and y would be the utilities of the Nash equilibria or the coordinates of the matrix.
Utilities, the actual values.
Okay, so in this case that would be 2 and 2.
I don't have access to the game right now, so whatever you say, I don't know.
For prisoner's dilemma, the Nash equilibrium is 2 and 2. So in 10x plus y, we'll put 2 and 2, right? Okay, thank you, ma'am.
Yeah. Okay, so let's move forward if there are no further questions here. Let's take other matrices. This was the simplest one. So there could be other scenarios, like for example this one. There are two hunters, they have gone to hunt and they have two options, either to hunt a deer or a rabbit. Let's say they can hunt only one of them at a time. And if they can coordinate, they would have gone for deer. But if they can't coordinate and they're supposed to decide based on whatever judgment they can make, this might be a very different scenario. So let's try and find the Nash equilibria for this and verify if that really is an equilibria concept or not for the particular problem. So I'll give you guys a minute, try doing it either way you want and see if you can identify what should be the equilibria for this particular problem. Hold on. Let everybody try. Whether you've seen the lectures or not, give it a try and then we discuss it. Give it 1 minute.
Is this minimization or maximization?
Right, maximization. Both are maximizing.
Dear dear seems to be the the equilibrium thing.
Is that the only one?
It could also be half 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 comma half, like
Yeah.
this rabbit rabbit.
Yeah. So the inequality that you'd be using, since it's a maximization problem, is going to be the opposite one from the actual definition.
But how difficult is this to compute Nash equilibrium, and would it always be possible to get the Nash equilibrium in this situation?
So it depends which Nash equilibrium we are talking about. If it is the kind that we are talking about right now, where either it is deer or it is rabbit, then sometimes there may not be a Nash equilibrium. But if some kind of a randomization is allowed on top of it, like saying, you know what, I'll try and go for both. I'll give deer like a 30% of my time to try and catch it. If not, I'll give my remaining 70% time to catch that rabbit. If you can split like that, or if you can have randomization, then in non-cooperative games there is a theorem, it will eventually come up, that in such a scenario there will always be a Nash equilibrium. So in principle it exists, finding it depends on the difficulty of the problem itself. Okay, so now two things have been said, right? There are two possibilities, either it's deer deer or it is rabbit rabbit. So you can look at it in the following way. You can assume that you can start by saying that you're looking at what hunter 1 does in the beginning, and say, okay, it is assuming hunter 2 has chosen deer, and then look at its own payoff. So now it's looking at 2 and 1. Between 2 and 1, since it's maximization, it would prefer deer. Similarly, if it looks at the other one, between 0 and half, it would prefer half. And now let's do it for the other agent. So now let's say we are talking about hunter 2's scenario, and what would he be doing? So he would be comparing this 2 and this 1, if he assumes the other one has actually chosen deer. In that case, 2 is preferred because both are maximizing. And similarly, for this case, he would compare 0 and half, and hence would say half is better. So in this case, we got two equilibriums. And whatever I said by just highlighting in this matrix itself, that was pretty much this equation. How was it this equation? I kept the strategy of the other guy constant. Remember, when I was talking about hunter 1, I said, okay, let's say we are talking about hunter 2 being deer, so we only focused on this part of the matrix, and then I compared what happens in the two scenarios, which is better, that must be it, which is better, let's note it down, and then went through all the possible combinations and then found out which one it is.
And how valuable is this to get Nash equilibrium? Once I got the Nash equilibrium, would it be a valuable thing or what? So what is the implication of showing the existence
It's
of
like
Nash
saying,
equilibrium?
what is an optimal decision for the players to take if they were to follow the rules of the game, the rules that are assumed in game theory, then what must they have done, or what must they do? That's what we're getting to know. So we're getting to learn a little bit about how decisions are made when, let's say, players are sticking with their objective. So if they are deciding to maximize, they're sticking with it and they're rational about it. That if something is better than what they have, they would go for that other option.
Oh, all right. And
Yeah.
do we have game theory for the irrational agents as well, wherein one agent is trying to maximize his benefit and trying to minimize the other's benefit simultaneously? Do we have game theory for such scenario as well?
So from what I understand, basic things, the basic formulation can be generalized to that as well, because we're just changing one assumption and then looking at it. But whether that is actually being done or not is not something I'm aware about. So I can check that and I can tell you next time.
Oh, sure.
Alright, so far we've seen very simple games, and these were the games, these were the scenarios that were there in the lectures itself. So now let's take a few steps forward and try doing some more problems. So I'm taking to the next case. So now we have two agents. Let's stick with two agents. Three would be still a little too much. Let's get comfortable with this first. And now both of these agents have three strategies available or three actions available. But look at the labeling of the strategies now. The labelings are different. It's LMR and TCB. So right now the strategy sets are different for both of them. Player 1 cannot take the action L, for example. Okay. Now, well, in this particular question I'm asking to find Nash equilibrium using a particular strategy, but before we go into that, let's try doing it by highlighting in the matrix itself. If you have a pen paper available, you can try doing it and you can tell me what are the possible answers, if there are any, or how about write in the chat box so everybody at least gets a chance to participate.
Maximization and minimization.
You can assume maximization if it's not being said.
Okay. So for the player 2, if the player 1 goes for the option B, then the player 2 would be having max payoff. But the player 1 would be having least payoff.
They care about only maximizing theirs.
Oh,
They're not comparing from the whole box. From the whole box, if they were comparing, then there should be some sort of a way they can take anything. They can't do that. They can only change their own actions. They can't change the action of the other. They can't even tell the other to, take some other action. There's no. So far, we've not talked about things of that kind.
and we want to maximize the payoff for both the players?
Yeah.
Or, okay, for both the players. Right.
Okay. So, should I go ahead and do it? Or you guys want more time to try?
Ma'am, I think the answer should be 2-1 and 2-1.
Uh,
Please.
so, you're saying this one and this one?
Yes. Yeah.
Okay, let me quickly verify. Anyone else has any different answers or something else to add here?
So it could be 3 comma 1 as well. So then the player 1 would be getting the payoff as 3 and then as 1. The total sum came out to be 4, better than the.
Okay, we're not bothered about what is the total sum, okay? That is not the objective. The objective is individually they're just maximizing their utilities.
So if 2 comma 1 is a potential solution and if the player 2 is getting the payoff as 1, then it is better that the player 1 gets slightly better than what player 1 is getting in this 2, 1 combination. So player one could have gone to see better options, three, better
Mm-hmm.
value three.
Yeah.
So then 3, 1 is better than this 2, 1 in that
Hmm.
sense.
So for the first one, for this one, I don't think this can be a Nash equilibrium. Simple reason: if player 2 had played L, player 1 would benefit from taking C. So it would prefer going to 3, 1. So it would shift from here to here. So this can't be a Nash equilibrium. Okay, so we can check for the other one, but okay. Similarly, let's go through the next column. Second column, again, player 1 would prefer playing T, and in the last column he would again prefer playing T. Now I am going row wise, so I am looking at player 2's scenario. Player 2 for first row would prefer R. So yes, this is a Nash equilibrium. For C, it would prefer R again, this R again. So we have one Nash equilibrium, which is 2, 1 in this case. We got it by actually using the definition. Okay. Now, as a part of this question, we are being asked use the method of iterated elimination of strictly dominated strategies and then see what do you get. So let's take a recap of what these things are. Dominated strategy means the strategy which by default is performing worse than something else and strictly performing worse. So in this particular scenario, or in general, so since we are in the case of maximization, so I am writing it as if xi is worse, then let's say some x hat I, this is what would happen, and this would happen for the specific player we are talking about. But this would happen for every xi, x minus I. Meaning, so now what we are considering is, we are comparing, let's say we are focusing on player P2. So P2, notice something here, P2 performed well if it took R in all the three scenarios, right? 1 is better than 0 or 0, 1 is better than 0 or 0, 2 is better than these two, this 2 is better than these two. Meaning R is actually the preferred choice for player 2 if he was being rational, if he was trying to maximize his utility. Which is like saying these two are the strategies which are dominated. So in this particular language that I've written, this is like saying the utility of player 2 for R given the utility, any utility for player 1. So let's just call it x of 1, whatever that strategy is chosen to be. If we compare it to L, this is greater. If we compare it to M, this is again greater. x1. Here x1, let's say, is something from TCP, and this is true for all x1. So in other words, I can say R strictly dominates. So strictly means I can have a symbol like this. R strictly dominates L. So now I'm comparing the strategies, and R strictly dominates M. Okay, this is the first thing that I've noticed here. Is this clear?
Yes, it's just because that all the values in the column R are greater than the values in the column.
Huh. The comparison between two strategies is based on the utilities. I've written the utilities as utility of the second guy, comma, the utility of the first guy.
Right.
Right? So what was this particular process? Elimination of strictly dominated strategy. So here L and M are dominated, and they're both strictly dominated. So we can remove them. We can remove one at a time, or we can remove both of them. Correct? So let's just do the easy thing. Let's remove both L and M. So now we are eliminating these two. And why are we eliminating them? Because these are both strictly dominated by R. Okay, if I do that, let me just copy this. Question, right? Or just hold on for 1 second. Okay, so if we are supposed to eliminate, let's just get rid of them. So L is gone, M is gone. So all I'm left with is this last column. So now player 2 has nothing to choose from. Player 2 is just going to be, the strategy of player 2 is just going to be R. The only option is with player 1. So now player 1 can just choose whichever maximizes his utility. And in that case, he will go for this one. Or in other words, we can say we'd eliminate C and B because those are strictly dominated by T. So second step is, so this was step 1, this is step 2. So here he's going to, this is player 2's doing, this is player 1's doing. He's going to eliminate C comma B because these are both strictly dominated by T. And what are we going to be left with is just 2 comma 1, which is the Nash equilibrium. So this is an example similar to what was done in class also in the videos, where we have taken a game. We have used the logic of assuming that everybody is rational, or that everybody is going to maximize, and they know that that's what everybody is going to do. So it's common knowledge that rationality is there. Then we are eliminating strictly dominated strategies, the ones which underperform, strictly underperform, those are eliminated. And in the process of doing that, we end up with just one unique option, and that option T comma R becomes the Nash equilibrium. So we've gotten the same point by two different methods. Okay, so let me highlight, this is not a Nash equilibrium, this was incorrect, this is correct. Is the process clear? we are first identifying if there are any strictly dominated strategies. If there are, we know that the order in which they are removed doesn't matter. So we just remove them either one by one or all of them together if we want, doesn't matter. And whatever we are left with at the end of this iterative process is going to be a Nash pair. Any questions here?
So maybe this dominated strategy is playing the role of constants in that inequality. Because once you identify that okay, these are the dominating strategies, that then from where do we get the interesting things? So we will get the interesting things from there, wherein there are no fixed things.
Yeah, when this
Like,
doesn't happen, that's where the problem is more interesting. This is the easier problems, easier game theory problems.
yes. So
Okay, so shall we take another example of this? Or if everyone is comfortable, we can move forward with the theorems and the things that were discussed in class.
so you can move to the next one.
Okay, people spoke at the same time, maybe one by one.
I think we should move for the theorems because we have just 45 minutes left for the.
Okay, sure. Okay, let's continue. Okay, so another thing, this was done in class. Same thing was done, but here the dominated strategies are not strict, they are weak. For example, you can notice the comparison between T and M. Between T and M looks better here, but when we compare for this scenario, they're both the same. So this is where the problem is. This is no longer strict. Here it's still better, so okay. So right now I'm only comparing between T and M and saying that M is either always better or at least equal to T, meaning this is no longer a strict domination. So in such a scenario, if we eliminate something, what happens? This was demonstrated in class. So I'll quickly go through the two paths that were explained. There are a few more variations that are possible in this particular problem. Okay, before we get to that, let's identify the Nash in this particular example. So I'm looking at the rows first and then columns. So I'll start with rows. These two are the best options in rows for player 1. These two are in the next row, sorry, in the next column, and this is the last one. So this is all for player 1. I have highlighted the best option possible. We're maximizing. Then for the other player, the comparison is row wise. So these two are the best options, or these two, or this one, which means we got 1, 2, 3, 4 Nash. But if we go by the process of eliminating, we would end up eliminating things that may actually be relevant in terms of the fact that they may actually be Nash pairs. Okay, so let's consider the first path. The first path is, we are saying M is the dominating one, weakly dominating one, or T is dominated. So this process removes T. So we are left with just this part of the matrix, meaning we already lost one equilibria here. So one path that we could try is that we don't eliminate T. Then what we did next is, this is the first step. In the next step, we are comparing R and L. We are comparing these two. And in this comparison, oh, have I written it wrong? Three, two, 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 1, 0. Oh, this looks like I have the values wrong somewhere. Okay, I'll do this. So now if we compare R and L, R is the one that should be eliminated. Sorry, L is the one that should be eliminated. If we are eliminating L, that means we are losing these two also. So the only option that we are left with is MR. Okay, hold on, what happened? My bad. So if we have eliminated T, all we are left with is this component. We are not supposed to look at the first row anymore. In that case, this was originally 0, right? L is better, which is what it was. Strategy L is weakly dominated, meaning we can remove R. If we remove R, this is all that we are left with. And then we can compare B and M. In the comparison between B and M, it's comparing so M is better than B. So we can remove B. So we removed this last one also. And we're left with last these two options. Between here we'd end up with the Nash equilibrium, which is ML. We could repeat the same process and go with different paths. So let's try one more different path. These two were there in class. Let's try one more different path to get any of the other options. Where can we start? Any suggestions?
Can we start from, like, let's say 2, 1 at the center?
You want to compare center with?
We can compare center with, like,
R or L?
with, let's say we compare it with L.
Oh, with L it's not a good comparison. See, here it's 3, 2, so this is better, but here it's 2, 1, so this is better. So this is not a comparison. We can compare C and R. Right? 3, 3, okay, both are fine. 1, 2, this is better. 0, 0, okay. So this means this is weakly, which is what we are going for. And we can remove C. Okay, if C is removed, this is all gone. Now what can we do next?
We can remove B after that.
How can we remove B?
So
See,
the-
for B you would be comparing let's say we compare B with the, okay, okay, we can compare B with M, it's fine. So these are both 2, so each is fine, but between these two, B is worse off. So between B and M, B is dominated strategy as compared to M. So we can remove this also. So now we are left with this portion and this portion. Next, what can we do?
I guess we can remove T. If we compare T with M, then we can remove T, because in both the cases, in the leftovers, I think
We can't compare
T is worse.
T and L, right? They're for different people.
T and M.
T and M. Oh, okay, okay, okay.
Only the leftover portions, because 1, 2 is always like lower than 2, 2, and 0, 3 is lower than 3, 2 in the leftover.
So, yep, T is worse than M. Yeah. So let's remove T. T is gone, C is gone, and B is gone. So we're just left with this or this. Player 1 has no choice remaining. It's player 2 who has a choice. So player 2 would choose between L and R, and he's actually okay with both of them. So what we are left with is the block L, R and M. Oh, but we got the same ones. Even by taking a different route, we did not manage to capture this one or this one. You can try other combinations. There should be a combination with which you can get these two also. But the point that is to be noted here is when we are dealing with weakly dominated strategies, and those are the ones we're eliminating, we don't have a guarantee that we will capture all the Nash equilibria in one go. And we will get one of them, but we won't know if that's the unique one or not. We'll have to go through all different variations of removing. Only then we can be sure. Okay. So with this, we've sort of covered a few examples. We've sort of gone through the main points. If there are no questions, I'll briefly go through the theorems and just describe them. I will not be going through the proofs. Okay. It depends which kind of a scenario you're talking about. Payoff can evolve with time, but we are taking a scenario where that's not the case. Actually, throughout this course, we are assuming payoffs are not changing. They are constant in time. So if you were to think of these kind of games in a ML or AI type setting, for example, a recommendation system, every time something is suggested to a user and that user actually accepts that request, for example, order something that was recommended by Zomato, in that case the payoff changed. The idea of the recommender system itself changed, and hence the payoff will get different. So it can change with time. That's one very vague example, but we are taking a simpler case for the time being.
Like in the setting of modeling and ecological system, wherein the things are evolving over the time, the species are evolving over the time, and so certainly the payoffs are likely to be changed.
Yeah, they should.
Oh, I see. All right, thanks.
Yeah. Okay, so okay, let's do one thing. I have one more example, but we can do it at the end. Let's first quickly go through the theorems. Okay, I'm starting out with the definitions, I guess. So one of the definitions that we've already encountered and we've actually even dealt with is strictly dominated strategy. So a strategy xi for a player I is said to be strictly dominated for that particular player if there is another strategy from that same strategy set for that player for which, for this other one, the payoff is better. So now the better is defined in terms of minimizing. Typically you'll see in the course wherever there are theorems, it's minimization that's being talked about. Okay, so all of those definitions are in that respect. So what this definition is saying is that a strategy xi, if we compare the utility of agent I where the strategies by everybody else is fixed, the only thing that changes is the strategy of this agent I that we are talking about, and we compare it with some other strategy from that strategy set. If we can find another strategy that does better, strictly better, so never equal, always better, then we call that as a strictly, we call that xi as a strictly dominated strategy, and this needs to hold for all the other options, all the options for the other agents. That's why here when we were comparing, when we were talking about strictly better or not better, for example, then comparing C and R, we looked at what happens, what is the comparison of these two for one action taken by the other guy. Then we looked at the other action, we looked at all of them, and only then we managed to say that okay, this is better, this is better, this is better. That's why we went on to say that R is better than C, irrespective of what the other agent has done. So irrespective is important, and that irrespective shows up in the definition in the form of saying it's for all the other x minus i's, for all the other x minus I strategies, meaning the strategies of the other agents. Okay. Now the weakly dominated strategy just says that for all of them this is true. So there might be equality in certain cases. The only difference now is the strict inequality term is true at least for some of them. Again, as we saw here, this was the example of weakly dominated. We already saw that 3 and 3 are equal. So for agent A's, agent 1's action being T, these two are the same. The strategies C and R are actually the same thing. But when we compared the other ones, we saw that okay, R is better. R is better or equivalent to C. So in that sense, R was dominated strategy, but this was C is the dominated strategy, but this is a weakly dominated strategy. So it has to, the equality can hold for as many as possible, but the inequality has to hold for at least one of them. Otherwise, we would say that they are equal. They are not dominated by one another. Then we can't eliminate them just like that. Okay, so these are the definitions. Now,
So I have a query here that just because say this one strategy is dominating the other, then why to keep the other strategy? Simply eliminate it and then reduce the size of the game, reduce the size of the matrix, and then ponder upon the remaining stuff.
yeah. So if we are in a situation where we have strictly dominated strategies, right? Meaning, for example, here I am thinking, yeah, R is always better than M. Then I know player 2 will not play M. It makes no sense to play M. But this is strictly dominated. But if it was this type of a scenario, again we are comparing C and R. Now in this case, player 2 can still play C. C is just as good as R if we are restricting ourselves to one particular action taken by the other one. If we had, somehow we knew that the other agent is actually going to play T, then it doesn't matter, they are equivalent. So we can't just eliminate them directly, and we saw this, right? If we eliminate them, if we eliminate strategies which are weakly dominated, we might end up in a situation where we're not getting all the equilibria of the game. Like in this game there are 4 of them and we have only managed to capture 2. So that can happen if we are dealing with weakly dominated strategies, and those are the ones we are eliminating.
Yes. Like in many examples, we had multiple number of national equilibriums.
Yeah.
So how good is this that instead of one now we are having multiple equilibriums so that we can take multiple decisions and we have more liberty and
So
more space of making decisions.
So you can think of it, in the form of some sort of a function. That function might have more than one minimas. Having more than one minimas can be beneficial depending on what you're trying to do with it. Right?
Okay.
If with just one action you end up, if with change of one action of both, you end up in a different minima, then they're fairly close enough to each other. What
Okay.
applications can you create out of that? So it's that kind of idea.
Can we compare multiple Nash equilibriums that this equilibrium is better than the other one, that sort of thing?
See, I am understanding that you're asking comparison of Nash equilibria in terms of, comparing the utilities, maybe some sort of an objective function on the utility values. So for example, taking the sum of them. So in that sense, this looks better than this one. But that needs to be defined very carefully. What is the objective that you're trying to look at? Then you can say which Nash equilibria is better than the other one. But so far, these are all just Nash.
Oh, all right.
There is one more way of looking at or comparing Nash, which is in terms of which is more risky, which is more stable. But we'll come to that in the main lecture videos also eventually.
Thanks.
Yeah. Okay. So these were the definitions for strictly dominated and weakly dominated strategies. Now, when we talked about all of this, we talked about something called rationality, and we said that rationality is assumed to be common knowledge. There was a rough definition given of common knowledge, which is just saying that each player, let's call it player I, knows that some other player I2, or maybe the same one. So it's saying that player I knows that player I2 knows that player blah 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 blah, and it goes on till everybody knows that event. So if that event is known to everybody, and that is known to everybody, and that is known to everybody, and so on, then that kind of an event is called common knowledge. Meaning, in our particular scenario that we have so far, the matrix, the payoff matrix, is something that is known to all of them. 1 minute. The payoff matrix is known to all the agents, and all the agents know that it is known to all the agents. Meaning, whenever they are taking decisions, they are taking decision knowing that the others have also seen this, and hence they'd be taking decisions based on this. So this is also known to them. So that's in some sense a common knowledge. Like there's a iterative recursive type of a scenario here. Yes, there was a question. Is someone speaking? Okay, so whoever had a question, you can interrupt me or you can raise your hand again. Yes, ask. Is this that kind of scenario? This person is raising his hand and exiting the meeting or something? Okay, I'm just gonna continue. Alright, so now we're starting with the theorems. So this is the idea for the remaining 30 minutes. I'll go through the theorem statement. I'll explain the statement in the exact form first, and then try and give you like what does it mean in English. What does it mean, and if we have already tried using that idea. Okay. So at this point we have seen what a game is, what Nash equilibria is, what this strictly or weakly dominated strategies are, and finally what is the meaning of common knowledge. By the way, here we have not talked about what does it mean to know, Like, see here we are saying this player knows that this player knows, and so on. We have not defined what does know mean in a formal way, and this is something that will come up in the next week's lectures. This is going to be a part of common model and so on. So then this idea of common knowledge will become more concrete. For now you can think of it like a recursive statement. If you guys know the reference, maybe you can think of Joey making a statement like this. Alright, so now let's go to the theorems. So this theorem is talking about two games. The only difference in these two games is the strategy space, and what we know is this S hat is a subset of Si. So we're by some logic we are eliminating strategies. That's all this is saying. That's the game G and game G hat. This particular theorem says if X star is a Nash equilibria of the game G, and this particular strategy for each player is available even in this S hat, meaning after whatever elimination you have done or whatever logic you came up with to reduce your matrix, if the equilibria still lies in the game, then that is going to be a Nash equilibria of the reduced game also. So this is the original game, this is the reduced game. So all this is saying is, if in the process of eliminating something from the matrix, so let's say we had these many things, we eliminated this row, and we're left with something. Whatever is the equilibria in that reduced part, if it has the equilibria of the original one, so let's say the original's equilibria was over here. If this is still present, this would still be an equilibrium even in the reduced game.
So then this is as per the common knowledge also, common sense also.
This is a trivial theorem, because you're reducing in a way that the best one is not getting removed. Like whatever your logic may be for removing it, but that is still present. If that is present, that should still be the best one. That's all it's saying.
Yes, right.
Okay, so now let's go to the next theorem. The next theorem is, now this is related to the process of elimination, which particular process we are referring to. So this is saying, let's say there is a G hat which is obtained from G by elimination of weakly dominated strategy. So this is the key point here. Then everything that is a Nash equilibria in the reduced game will be an equilibria in the bigger game. So what it is saying is, this is the original game, let's say this is G. After reduction, let's say I have removed these two, so I am left with two rows and one column, 2 rows and 3 columns. Then let's say this particular one in G hat is known to be the equilibrium. Then this statement is saying this would also be an equilibrium even in the original game. So let's say this one refers to this particular box.
And what we removed from the original game?
We removed weakly dominated strategies. So we have kept the dominant ones, the strongest ones are still there.
So
But
will it hold in the other direction as well? Like say, will the Nash equilibria of G would be preserved or would persist?
okay, you
if
tell
the
me
G
the
pair
answer
is-
to that. We saw an example already.
Yes, yes. So
So
that will be preserved, right?
no, no, we saw, right, this example, there are 4 equilibria, but after elimination I only get 1 or 2 depending on which path I chose. So
Yes, yes,
it's
right.
not going to preserve all of them.
True.
It's the opposite point that is being made in this theorem. This current theorem is saying if there is an equilibria in the reduced game, so for example ML, this one, this would also be an equilibria in the original game, which is what we saw. That is happening. That is correct. Okay, so let me come back to the theorem again. So this theorem is in the direction, if we find an equilibria in the reduced game, that will also be an equilibria of the bigger game. The way to justify this is that we would not have removed the most dominant strategies. We would not have removed the best ones. We would not have removed all the best ones. There has to be at least one strategy which is better than the existing ones, because what we are removing are the dominated ones. So whatever we are left with, or whatever we have in whatever is the equilibria in the reduced game, would have actually come from the original game itself, meaning no new equilibrias are getting created. Okay, we may not get all of them if we are going by weakly dominated, but nothing new will come up in the reduced game if the process of elimination is by weakly dominated strategies. So that's the key point, that's the takeaway of this theorem. No new
Right.
EQ means equilibrium.
So yeah. So is there a way to quantify the relevance of a particular column? Like say like in this reduction process, so we understood that some of the columns are more important than the other columns. So is there a way to quantify that okay, this column is more important, this strategy is more important. So if I remove this column, then I'm going to lose this much of the information.
We're
So quite possible that if I remove one of the column, then still I may keep the information preserved. That is what probably the meaning of one of the theorem you explained is. And in some of in the other theorems, if I remove some of the columns, then certain things are not going to be preserved, and we may incur information loss. So is there a way to quantify this entire stuff that okay, this column is more important than the other columns, and this much information is going to be lost if you remove this column?
okay, so there is nothing being said about information here. What is being said is in terms of strategy. So one strategy is better than the other in terms of the comparison of the utility, which is what defines these dominated strategies, or the exact opposite of it, dominant strategies.
Right. So I mean to say, to what extent can I compress a game? To what extent can I compress the matrix of the game? And still, let's say the most of the things are going to be preserved. That sort of a thing. I mean, information loss, like say potential use of the information theory in the game stuff, wherein I can at least quantify that okay, this column or this strategy is more important than the other strategies.
See, if you are doing weakly, if you're eliminating weakly dominant strategies, you can either end up in a situation where you're left with just one thing at the end, one particular profile, or you could be left with more than one profile, and they're both equally good, and you can't eliminate anything further. So all of those situations are possible depending on what is happening in that particular game. It depends on the utility of that particular game.
Oh, okay. Yeah, thanks.
Yeah. Okay, so this is a general theorem, this last one, which is just saying if the equilibria is present in the reduced version, if the profile is present in the reduced version, which is the equilibria in the original one, that same thing would become an equilibria in the current one also. And we already saw that happen no matter which way of eliminating we choose, whether it was weakly dominated or strictly dominated. We saw that happen in both the cases. Now this is the slightly more interesting result. This says if we are eliminating by weakly dominated strategy, if we are removing weakly dominated strategies, then whatever we get as the Nash equilibria in the reduced game will also be a Nash equilibria of the original game, meaning nothing new, no new equilibria will get created in the process of elimination the way we are describing it. Okay. Now let's go further and talk about what happens when we are doing elimination of strictly dominated strategies. So if the elimination is using if we are eliminating strictly dominated strategies, then both G and G hat will have the exact same number of equilibria, the exact same equilibria itself. So if the original game had only one, G hat would have only one.
Yes, trivial.
Exactly.
Seems to be trivial.
Meaning, if we are eliminating by this particular method, elimination by strictly dominated strategies, then we will find the equilibria in the original game in the reduced game. So it would be easier to work with the reduced game, and we would get all the needed optimal strategy profiles that we would have gotten from the original game. So this is what this particular statement is saying. So, so if I were to make that little drawing, suppose and we are eliminating, okay, so we'll most likely eliminate this one and this one. So what we would be left with would be right after eliminating the ones that I've pointed at. In that sense, the set of equilibria is equal in both of them. So nothing got destroyed, nothing got created if we are using the process of elimination of strictly dominated strategies. Now we can ask the next question that okay, suppose we are actually doing this, and at the end of the process we're doing this removal by removal of strictly dominated strategies, and at the end we get one equilibria. So instead of two, we just get one. If that is what happens, then we can say that that particular equilibrium is actually unique in the original game. We got two, so we can't say anything further, right? But if we got only one, so if the process of iteratively removing would lead us to that one unique equilibria point. This is specifically true if we are talking about removing strictly dominated strategies. But on the other hand, if instead of strictly dominated strategies we removed weakly dominated strategies, then we would get one equilibria from the many. There might be more, we don't know. We cannot say if that is the only one, because it would have removed a lot of things, and we saw that in the example. So in short, what this is also saying, what these two corollaries are also saying, is that in this case the order of elimination doesn't matter, because we are going to end up with that exact unique Nash equilibria if there is just one. If there is more than one, we'll end up with exactly those, and maybe the specific strategies that we can't remove any further, like that can't be reduced any further. But the order of elimination won't matter. But if we were to go by the process of removing weakly dominated strategies, order matters. So with this, with this I've covered all the theorems and corollaries that were there in the course. Anyone has any doubts in anything that I've talked about today?
Any book which you can suggest and which is not the thick one, any thin book and having all the necessary stuff, and which I can read in 2-3 weeks.
If you prefer, reading sentences over reading math first, then maybe Meyerson might be a good fit for you. Game Theory by Meyerson. If you can, make yourself be comfortable with the math, just look at it for a while. It starts to make sense in some time. If you can do that, then this one. I know the short form. It's MSZ. That's the book that you should try. In fact, both of these books are mentioned in the suggested references, so you can look at the exact names. But I would recommend, so if you're comfortable with having a story first and then the theorems and the math, then try Meyerson. It doesn't have all the topics that will be covered in the course, but it will be a very good starting point. Else, focus on using MSZ.
Okay. Thank you so much.
Yeah. Okay. Anyone else? Any doubts? All right. So.
Thanks a lot for the. Thanks a lot.
Yeah, sure. So I'll quickly take a quick summary of whatever we talked about. If in the summary, if you have any doubts, you can ask still. Okay. So from the whole thing, you must have noticed the crux of this particular week was to get a first-hand flavor of what are games, what kind of games are there, and two particular ideas. One is Nash equilibria and the other is this idea of dominance. You must have already noticed dominance may not always be there. Okay, yeah, wait, I had an example for that. Like there may be scenarios, there may be games where you can't say anything about is there a strictly dominated strategy or is there even a weakly dominated strategy. So such situations are possible. In these situations, then you have no choice but to just use Nash equilibria concept directly, the definition directly. Otherwise, you can use one of the process that we saw today. Either go for elimination of weakly dominated strategies, there you just have to be careful because the order matters. Or if there are strictly dominated strategies, elimination of those will help you get to the answer as fast as possible.
So here I do not find any strictly dominated strategy. Neither of the big people.
Yeah, exactly. That's not there. So the quick way to know that is you can go column wise and then row wise. So column wise, if you go, you'll see this is the best one. Let's say we are maximizing everything. Sorry. So here, just by doing column wise, I can already see for each strategy of the other guy, my best choice is changing every time. So this one is going to not be very easy to solve, but nevertheless, so this is for agent 1. Now we can try for the other agent. So we can compare 2, 1, 0. So that means 2 is the best option. This is the best option. This is the best option. So the point of this example is that this does have Nash equilibria, but we can't get to those by using either of the iterated processes that we saw. We have to just use the definition. That's the only way.
And what is the complexity, usual complexity of the algorithms and which are trying to find this Nash equilibrium
You have to
programmatically?
you have to search over the whole space, right? It's n square, at least n square.
But then not only I have to search the entire space, I need to make a lot many decisions as well. That okay, corresponding to the row and then that stuff. So I okay, but then would be polynomial.
Mm.
Do we have some undecidable problems related to the game theory as well? That those problems which have proven to be unsolvable.
Unsolvable. So by solving, do you mean finding a Nash equilibrium?
Any problem in related to the game theory, and for which we have a mathematically rigorous proof that howsoever hard we try, we can never ever solve them. So basically, I was just thinking. I mean, game
Okay,
theory
I
from the
have an
complexity.
example. It's just that the example goes out of the scope of this course, but I'm gonna mention it since you're asking. So there is something called LQG control problems. In those, you just can't optimize it. There are more than one agents. There are 2 agents, and they have to take actions based on whatever they see. So there's some uncertainty involved. It's in a slightly different way. There, people have still not managed to optimize it, given the information is in a certain way. So the term is, if the information is non-classical, then what is the best strategy? People still don't know that, and it's been around for a really long time. It's called Witzenhausen's problem. I'll just write these words in the chat box. If you want, you can look them up. Witzenhausen's
This
counter example. This is LQG problem in non-classical information. So this is going in a very different direction. I don't expect you to understand, but if you are interested in, so this is one of those very classic problems, but very hard to solve. Very hard to solve in the sense people don't know what's the best strategy in a scenario like this, and it's a very simple scenario. So yeah, you can have a look at it if you want.
thanks.
Alright, I'll quickly summarize, then we can end the session today. Alright, so we started talking about what does the whole idea of game theory even is. We started with a very simple game, which is this rock paper scissors game, and then we go on and say that, well, a lot of other scenarios, maybe from politics, maybe from negotiating, or even from biology, can be modeled in the framework of a game. And in the process of doing that, typically what is required in a game is that it will have a number of agents, the strategy set for each of those agents, and the utility for them. So all of that ends up being captured in this following way. So here we have the agents, here we have the actions or the strategies for the time being, and this matrix becomes the utility matrix that we require. Almost throughout the course, we'll be talking about scenarios of non-cooperative scenarios where the agents are not allowed to communicate. And in those scenarios, they're supposed to take their decisions, they're supposed to choose their actions without knowing what the other one will do, and they have no way to tell each other what they are going to do and hence what the other one should do. In this particular kind of a game, this matrix, the utility matrix, is known to all the agents, and it is also known that all the agents know it, meaning they can make decisions based on this. They don't have to put some beliefs on top of this. This is known to all of them. So this is common knowledge in that sense. Then all of the things that we're talking about is not from the point of view of helping a player come up with the best strategy. It is from the point of view of an observer who is just trying to see what are the laws that describe problems of this kind where decisions are to be made by multiple players. Then we went on to talk about one particular concept of a solution here, which is called Nash equilibria, which says that no agent, so now this is something I'm going to just say it in English, I'm not going to go through the definition. It just says no player benefits from unilaterally deviating from his action given the others are doing the best action possible. Okay, and we saw how this is to be computed in some simple scenarios. We can either use the definition directly, or we can point out the things which are performing better for each agent in the matrix and find out the Nash equilibrias. We saw that for a few examples, and then we finally saw the whole scenario of dominance. So first we started by saying what is a dominated strategy, or hence the dominant strategy, the stronger one. Then if after having identified all of them, if we eliminate them one by one, what happens? So we took an example of that, and we saw if we eliminate them one by one, we end up with a Nash equilibrium, and it goes exactly according to the theorem that we saw, that if there is one Nash equilibrium in the original game, that will be uniquely identified by the process of iterative elimination, and that's exactly what happened in this example. So there was only one equilibrium, which is this one, and it got identified by the elimination process. Then to have another enriching example, we saw this scenario where we are removing the weakly dominated strategies. So not the strictly dominated, now the weakly ones, meaning at some places the utilities might be similar. Yes, all problems that can be modeled as a game, these things are useful. So dominance may not always come up. I showed you just one example, but Nash equilibrium as a concept, it does show up. It's the core one. Okay, so in this particular scenario, we saw that depending on the route that we take to eliminate strategies, we would end up with different outcomes. Either it's ML or MR or both of them together. It depends on the path that was taken of elimination, like what was the order of elimination. So it's making 2 points clear at the same time. Even though in the original game there are 4 Nash equilibria, at the end of the elimination process, we don't get all of them. Either get 1 or we get 2. We're not getting all of them. And even if we get 1, getting 1 does not guarantee that this was the unique Nash equilibrium. We'd have to go through a few more paths, few more order of elimination to confirm that this is the only unique solution. Okay. Then we saw that there are possible scenarios where there may not be strictly dominated or weakly dominated strategies. In that case, just finding the equilibria by looking at the matrix is still possible. So next class it's going to be talking about this common knowledge from the perspective of Oman model, which will tell us what does it mean to know, that one player knows something about the other player. What does it even mean? What does the word know mean in a formal way? That's what is going to be defined in that model, and hence the definition of common knowledge will become more formal and strong. Then just to quickly repeat, this is saying that if we go to, from an original game, if we go to a reduced game and the equilibria profile is present in the reduced game also, then it will be still a Nash equilibria in that game, meaning it will suddenly not become a not Nash equilibria. That will not happen. So it will not get destroyed also. That's what this part means. It may be lost but not destroyed. So this is not destroyed. This is the second scenario where if suppose we are eliminating by removing weakly dominated strategies, then something that is a equilibria in the reduced game will be an equilibria in the original game also, meaning some new equilibria will not suddenly show up in the reduced game. It has to have been present in the original game to begin with, and only then it will show up, meaning nothing new, no new equilibria will get created. So you can think of this as some kind of a conservation law of a sorts. Then as a combined version of these two, if we are dealing with strictly dominated strategies, in that case the set of equilibria would be the same in the original and the reduced game. And this means if there was only one Nash equilibria in the original game, with elimination of strictly dominated strategies, we would get that as the unique equilibria in the other game also. While this will not be unique if we eliminated the weakly dominated strategies. And hence in this case the order in which we are eliminating matters, the order does not matter in this case. In this case the order matters. So yes, with this I have covered the summary. Okay, I can see a couple of questions. One second. I am not aware what is Free Fire games.
I guess this course does not talk about the development of
Yeah,
games.
this is not creating games. We are talking about the theory of games. So this is, for example, the closest it comes to games is things of this kind. Games like chess, or games like rock paper scissors, or any such games, poker or cards or something of that sort. It's not saying the equilibria is created. It's just saying that there is an equilibria in the game if we could model the game in this particular format. That's all. Okay. Anyone else? Any other questions?
Would you be uploading these notes and the recordings?
Yeah,
Thank
you will
you
get
so
the
much.
required links. Alright, then let's end the session. Thank you so much. Bye bye.
Bye. Thank you so very much for making so much effort. Thanks.
Yeah, bye bye.